Okay, we are going to show you a ACG analysis in action. This is a healthy subject. We're looking at a normal 12-lead ECG from a 25-year-old male. And just hitting playback here now, you can see this normal ECG tracing in front of us. Now let's go ahead though and look at some of the advanced ECG applications that we currently have running in the background and that we will analyze for various advanced ECG parameters. We're going to start with the signal averaged ECG application. And it's just catching up. We're about 23 seconds in. And we can see over here on the right the fiducial point markers, the beginning of the P, the peak of the P, and the end of the P wave to start. And then the beginning of the QRS, then the fiducial point where we detect the R wave, and then the peak of the QRS, and the end of the QRS, and finally the peak and end of the T wave. Let's look though at some of the plumbing behind that, and this really has to do with signal averaging. So let's look at the QRS specifically. Here's a QRS window. Basically what you see on top is the template, and then on the bottom is the new QRS coming in. We're about a minute and 5 seconds in. And over here, we're looking at the cross correlation between the template and the new beat coming in, the jitter, mean cross correlation of those beats that have already come in. We have a choice of using either cross correlation or cross covariance. We're using cross covariance in this case. We have a nice clean recording. Go back. Now let's look at some of the actual parameters that we will utilize in A-ECG. We can see over here on the left first the loops. We have the frontal plane, the horizontal or transverse plane in the middle over here, and also the left sagittal plane. And what we're showing there are the colors. The first 10 milliseconds of a loop is in red. The next 10 milliseconds is in yellow. The next 10 in green. And finally, the rest of the loop, the main part of the loop, is in blue. And then the T wave is shown as a white loop. So you can see that in all three planes. Those are useful. Those are normal looking loops to me, having looked at quite a few of these. So I'm not too concerned about his derived vector cardiogram. And we can also look over at some of the parameters. For example, the spatial mean QRST angle is 61. That's normal. And the Peaks angle is also normal. You can look at things like the spatial ventricular gradient. Again, too many parameters to really go over, but we have very few red flags here. And this is a typical thing for a normal looking recording. Let's go and look at the QT interval variability technique. We're looking at actually the first eigenvector, so a transform lead. Let's switch that over to lead 2. One of the first things to notice is down at the bottom, the tachogram. It shows the beat-to-beat QT interval variability in purple. And then just above that, in this case, is the beat-to-beat RR interval variability. And you can see that those align pretty well. These are coming from the template, the QT variability that you see up here. It's a template matching procedure. And you can see that nice alignment between QTV and RRV, which is very typical for a healthy heart. And we can actually also look up here on the upper right where we see the QT interval beat to beat versus the RR interval on the x-axis. See that sort of diagonal tracing? That's typical, again, for a healthy heart. Keep these in mind when we later compare to disease. Here we also are showing the QT variability index. You can look in the literature for how that's derived. It's basically indexing the QTV back to the RRV, and it's normal in this subject as well. All right, let's go over here and look at heart rate variability. This is again, just RRV with a focus on it. This is a simple tachogram, and then a histogram on the bottom left. And the upper right is a Poincare plot where you're plotting one RR interval against the next one in two-dimensional space. Then down below we have various power spectral plots. We can look at that in several different ways. We have a Lume periodogram, which we prefer, then autoregression, and finally also a fast Fourier transform as well. So we do it all three ways, but we prefer the Lume as our nominal. And that's a normal looking power spectrum for a healthy subject as well. Finally, we also have a deterministic technique. This is the determinant fluctuation analysis showing the alpha 1 and alpha 2 slopes. Again, look in the literature for that for those who are interested, but that can also be a helpful RRV parameter. Let's go over, here's a brief look at HFQRS. We don't really use this much in A-ECG, but basically what we're doing here is also signal averaging, and then we're filtering between 150 and 250 hertz, focusing on the QRS and deriving root mean square voltages, which are small voltages, and also the kurtosis, the shape essentially of those resulting to high frequency QRS complexes. Let's go in here now. Let's look at waveform morphology instead. Looks like we're just coming to the end of the recording. We have the P, the QRS, and the T waveform morphology. Basically, this is where we're using singular value decomposition on those signal average templates. We're deriving 8 independent singular values. Remember, the 12 ECG consists of 8 independent channels of information. And we can look at things like the PCA ratio of the T wave, which is essentially the second singular value over the first of the T wave once you've performed that transformation. And that's quite normal in this healthy subject at 7 and change. Let's go back and take a look at QTV. Remember how that looks when it's normal, and also the HRV, how that looks when it's normal in a healthy subject, and also the loops, well, how those appear in a healthy subject. We're seeing a normal angle as well. Keep these in mind as we go on to follow-up videos where we will deal with people who are diseased as opposed to healthy.